Welcome to our Engineers Newsletter live broadcast on energy saving strategies for rooftop VAV systems. I'm Mick Schwedler from Trane's Applications Engineering Department, and I'll be your host as we examine possible energy savings in these systems. Through our association with the American Institute of Architects, credit towards continuing education can be earned for viewing today's broadcast. If you're an AIA member, make sure you provide your member number to your local host before leaving today's session. In several states, this certification can also be applied to engineers' continuing education requirements. Please check your state's rules to see if this might be applicable. As we move through today's broadcast, we'll be looking at the entire rooftop VAV system and discuss some packaged rooftop units that may give you advantages in reducing system energy. Following that focus on equipment, we'll examine system designs, then move on to system optimization controls that allow us to reduce energy consumption. In addition to addressing these energy reducing options, we'll look at how the savings can be quantified and compared with a basic rooftop system. Following the presentation portion of the broadcast, we'll answer some of your questions. Please fax them in at any time to the number on your screen. To cover this information, we have 4 presenters, with 2 of them new to you. First on will be Justin Wieman, who is Product Manager for Trane's analysis programs, such as Trace 700. From our rooftop department, we're privileged to have guest star Phil Baggett. Phil has a cornucopia of knowledge about rooftop equipment and has helped many people apply these units. A familiar face to many of you is John Murphy from Applications Engineering. Well known for his expertise in airside system and humidity control, he'll lead us through some of the energy-saving options available to us. Finally, Paul Solberg's vast experience in rooftop service, support, and application will give us down-to-earth, practical knowledge concerning these systems. Today, we'll be addressing quite a number of topics quickly, so we're using a different format. Rather than attempting to have what we refer to as awkward transitions between engineers, we'll have the topic we're covering on the screen and also the topic that's on deck. Now, let me take a few minutes to frame a typical rooftop VAV system. Then Phil, John, and Paul will cover concepts to reduce energy use. A rooftop VAV system consists of a packaged rooftop air conditioner that can serve either a single zone or multiple individually controlled zones. In multiple zone systems, each zone has a VAV terminal unit controlled by a temperature sensor in that zone. A building automation system helps all the pieces talk to one another. So, what are the standard requirements for this type of system? First, we'll assume that the space comfort is to be maintained and that the base system satisfied the code or standard requirements. Next, local codes differ all over the country, so instead we'll use ASHRAE standards 90.1 and 62.1 as the basis for setting our typical system today. This choice has an additional benefit. If the project is considering LEED certification from the U.S. Green Building Council, both are prerequisites. So using them to define minimum requirements is a good start. We won't go into all the requirements or exceptions here, simply hit the highlights. Justin, please take us through these 2 ASHRAE standards.
Starting with ASHRAE 90.1, we'll cover a number of the mandatory and prescriptive requirements of the standard that apply specifically to rooftop VAV systems. I'll be the first to admit that this is not an exhaustive list, but applies to general rooftop systems. For example, an office space, school, or medical office building. Now let's look at those mandatory requirements. Our slide shows minimum equipment efficiency requirements for packaged rooftops. Please note that when both a full load energy efficiency ratio, EER, and integrated part load value, IPLV, are listed, both must be met at the standard rating conditions. There is also a mandatory section on controls. Thermostatic controls are required for each zone, not room, but thermal zone. In addition, there is a requirement for the capability of having a 5 °F deadband, which is the difference between when cooling is enabled and when heating starts. Once the system exceeds 15,000 BTUH, a number of off-hour control requirements become applicable. The first is that automated shutdown is required so the system can be turned off without human intervention. Any of the 4 options shown on the screen satisfy this requirement. Temperatures are required to be set back. Heating setback is required in most climate zones. The exception is in the hottest climates. On the other hand, cooling setback is required only in hot, dry climate zones, but in those zones it must be automated. Optimum start is required once the system is greater than 10,000 CFM. Phil will cover this later. In large systems, during off hours, the system must be capable of reducing airflow by isolating areas of the building. This ensures that the entire air conditioning system doesn't have to function to satisfy a small area of the building. In spaces that have more than 3,000 CFM and high occupancy, the system must be able to automatically reduce outdoor air intake when the spaces are partially occupied. However, this is not required if airside energy recovery is employed. We'll look at that energy recovery requirement in a minute. Now let's consider the prescriptive requirements of the standard. As we described in our May broadcast, economizer requirement is both system size and climate dependent. This map gives you a general idea of where they're required. There are lots of exceptions which we've included in your handout, but will not cover on air. Simultaneous heating and cooling is not allowed unless at least one of the following exceptions is met. From a comfort conditioning perspective, before reheating or recooling can be performed using new energy, the supply airflow in the zones must be reduced to the largest of the quantities shown here. Many variable volume systems can be designed and operated to comply with one of these airflow limits. You may do any amount of reheating if at least 75% of the reheat energy is site recovered or site solar. In systems where active humidity control is being performed, there are different exceptions, but the thought is the same. Reduce system capacity prior to using new energy for reheat. Again, reheat may be used at any time if 75% of the reheat energy is site recovered or site solar. Later on, John will show us how this exception can be used in VAV rooftop systems. Once the fan system power exceeds 5 horsepower, there is a limitation on system fan power, and there are VAV fan control requirements. Standard 90.1 nameplate horsepower limitations are based on system airflow and whether the system is constant or variable volume. There are credits for additional static pressure due to heat recovery, filtration above an inch, or systems delivering air colder than 55 degrees. Note, too, that the part load consumption of fan motors 15 horsepower and larger must comply with the requirements shown here if used in a VAV system. Many people meet this requirement by installing a variable speed drive on the fan. Finally, fan pressure optimization is required for systems with direct digital control. This will be covered in detail later. Energy recovery with 50% effectiveness is required when individual fan systems have capacities of 5,000 CFM, of which 70% or more is outdoor air. There are 9 exceptions. There's also a limitation on hot gas bypass, not hot gas reheat, but hot gas bypass. As Paul will discuss later, this is very inefficient. The hot gas bypass limitation applies to systems over 7.5 tons, and the limits are shown here. Moving on to the ASHRAE Standard 62, it requires that zone ventilation airflow be calculated, then corrected for the zone air distribution effectiveness. then calculated at the system level. During operation, to meet the standard's requirements, this system ventilation airflow can be dynamically calculated. Note that in a variable air volume system, setting the outdoor air damper to meet the design ventilation requirement, then leaving it at that position does not meet standard 62 requirements. As the system airflow is reduced, bringing in the same amount of ventilation airflow requires the damper position to change, resulting in a larger percentage of outdoor air at off-design conditions. ASHRAE standards 90.1 and 62.1 have minimum requirements for all of those areas listed on the slides. Not all of them are applicable in every situation, but by following these requirements, we have a compliant rooftop VAV system.
Thanks, Justin. Now, let's ask our team to discuss rooftop system strategies, beginning with the equipment. As we move ahead, you'll see a timer, the subject on deck, then a bell will ring, and we'll introduce the next topic. Starting out, we'll talk about the gear, the equipment that goes on the roof. Next topic, high efficiency.
Engineers and owners are increasingly conscientious of applying the most energy efficient packaged rooftop VAV system at the most effective cost. And there are several benefits that make higher efficiency equipment an attractive investment. First, reduced operating cost. An increase in energy efficiency of 1 point can result in significant savings over the life of the system. Potential energy rebates for equipment meeting utility guidelines for high efficiency. Rebates can potentially pay for the additional first cost of higher energy efficiency options, and the return on investment can be immediate. Meeting state-mandated energy codes. 2 states have adopted legislation requiring energy efficiencies based on the Consortium for Energy Efficiency's recommended level for packaged rooftop systems. The state of Maryland enacted legislation in January of this year requiring 10.0 EER on packaged rooftop units 20 to 80 tons, and California has adopted language in Title 20 requiring 10 EER for equipment 20 to 63.3 tons manufactured after October 1, 2006. Additionally, Connecticut is slated to adopt similar legislation on July 1, 2009 for all large packaged rooftops. Designing a higher efficiency system is also environmentally intelligent. Reduced energy consumption results in reduced greenhouse gas emissions. However, there are potential detractors to investing in higher efficiency equipment. First, there is generally incremental cost for the high efficiency equipment. And in some areas, low utility rates may mean either an extended or no return on investment over the life of the system. There are several options available with packaged rooftop units that lend themselves easily to designing a more energy efficient application. High efficiency supply and relief motors, additional evaporator coil rows, and condenser coil capacity. These optional features can incrementally increase the unit's energy efficiency over applications utilizing standard coils and motors. Additional evaporator and condenser coil capacity can also provide incremental unit capacity. To demonstrate the efficiency gain between standard and high efficiency rooftop systems, we can compare 2 50-ton units, one with a standard refrigeration system and standard efficiency supply fan motor, and one with additional evaporator and condenser coil capacity and a high efficiency supply fan motor. Because application requirements vary widely, we've chosen to use ARI rating conditions for both units. At these conditions, the standard unit yields an energy efficiency ratio of 9.6 and 604 MBH gross capacity, while at the same design conditions, a unit with additional evaporator and condenser coil rows and high efficiency supply fan motor yields an energy efficiency ratio of 10.4 and 644 MBH gross capacity. To compare the difference in energy cost between the standard and high efficiency systems, we've generated a system analyzer report. This comparison method is used only to emphasize the difference in energy cost between 2 like systems with different energy efficiencies. For analysis, we've selected the 3-story, 60,000 square foot office building. The system selected is VAV with reheat. We use the default settings for building type and exposure conditions. We also use weather data and the utility rate for the Alameda, California area. Using the energy efficiencies of the standard and high efficiency units at identical operating conditions, we can generate an HVAC energy cost comparison. We can see by comparing the two systems that the higher efficiency rooftop system yields an energy savings of approximately $1,000 the first year of service. Some would consider this savings insignificant compared to the additional first cost of the optional high efficiency components. However, over a 20-year system life, this represents a simple savings of around $20,000. When combined with other energy saving strategies that we will address later in this broadcast, the investment in high efficiency options becomes much more attractive. And in addition to energy savings, an environmental benefit is realized through the reduction of fossil fuel emissions. By applying the higher efficiency equipment in this scenario, System Analyzer calculates over 5,400 pounds per year reduction in CO2 emissions, nearly 6,000 grams per year reduction in sulfur dioxide emissions, and over 8,000 grams per year reduction in NOx. Naturally, the decision to invest in the incremental cost of the higher efficiency unit would be driven by a thorough system economics analysis, return on investment, and potential environmental impact.
Next topic, air-to-air energy recovery.
Air-to-air energy recovery refers to the transfer of sensible heat or sensible heat and moisture between two air streams. In rooftop VAV systems, the most common use is to precondition outdoor air as it enters the building for ventilation. An air-to-air heat exchanger is arranged to exchange energy between the outdoor and exhaust air streams. Sensible energy recovery devices transfer only sensible heat. Common examples include coil loops, fixed plate heat exchangers, heat pipes, and sensible rotary heat exchangers, or heat wheels. Total energy recovery devices not only transfer sensible heat, but also moisture. Common examples include total energy wheels, also known as enthalpy wheels, and fixed membrane heat exchangers. The most common technology used in packaged rooftops is probably the total energy wheel. When it's hot and humid outside, the wheel transfers sensible heat and moisture from the outdoor air to the cooler, drier exhaust air stream. This pre-cools and pre-dries the entering outdoor air, saving cooling energy. When it's cold outside, the wheel transfers sensible heat from the warmer exhaust air leaving the building and uses it to preheat the entering outdoor air. This saves heating energy. A side benefit is that the total energy wheel also transfers moisture from the exhaust air to humidify the dry entering outdoor air. This improves comfort, or it will save energy if humidification equipment is being used. Using air-to-air energy recovery offers the following benefits. It reduces cooling and dehumidification energy, and also reduces heating and possibly humidification energy. In addition, it can allow downsizing of these components. For example, in many applications, the addition of a total energy wheel allows the gas-fired burner or heating coil in the rooftop unit to be downsized, or possibly even eliminated if morning warm-up can be accomplished at the VAV boxes. However, there are some drawbacks that need to be justified. First, the wheel adds pressure drop, which can increase fan energy. The operating cost savings provided by recovering energy must exceed the increased cost of operating the fans in order to justify the cost of the energy recovery device. Also, routing the exhaust air back to the rooftop unit may require more ductwork and ceiling space than a system without energy recovery. When using energy recovery to precondition outdoor air, consider these following general recommendations. First, properly size the energy recovery device. In a mixed air VAV system, size this device to precondition only the minimum outdoor airflow required for ventilation, not the maximum airflow expected during economizer operation. Bypass dampers should be used to allow for increased outdoor airflow during economizing. Second, strive for balanced airflows. Duct as much exhaust air back to the energy recovery device as possible. The less disparity between the outdoor and exhaust airflows, the more energy can be recovered. On a related note, in a system with a smaller percentage of outdoor air, restroom exhaust and leakage due to building pressurization may result in very little centralized exhaust during non-economizer modes. In this case, energy recovery might not provide much benefit. Third, integrate control with Airside Economizer operation. In many climates, an economizer can provide the benefits of free cooling for much of the year. When the economizer is activated, air-to-air energy recovery offers no benefit. In fact, unless the wheel is turned off, it actually increases the cooling load by adding heat to the entering outdoor air. Achieving maximum energy savings depends on proper economizer operation and integration of energy recovery into control of the entire system. Next, decide how much cross leakage is acceptable. In a mixed air system, cross leakage between the exhaust and outdoor air streams is seldom a problem. Most of the air that returns from the space is recirculated as supply air anyway. For most applications, the amount of leakage is usually less than 5%. Finally, provide a means to control the capacity of the energy recovery device. During cooler weather, VAV systems may require a means to modulate the capacity of the wheel to avoid overheating the air.
Next topic, relief or return fan.
Economy in operation must include maintaining space pressure. It's important to remember that a properly pressurized building will be the most comfortable, not just the most economical and the least problematic. Maintaining a desired building pressure in the face of continuously changing supply and exhaust airflow requires an automated fan and damper control scheme and is paramount to proper building operation and comfort. For rooftop VAV systems with airside economizers, the quantity of relief air is controlled to maintain the space pressure. There are two configurations of VAV relief air systems, the central return fan and the central relief fan. Controlling space pressure involves coordination of these rooftop fans and their dampers. At the same time, it must be remembered that under a separate control loop, the supply fan is forcing air into the duct to maintain desired supply duct pressure. Let's look at a return fan system first. The return fan, which operates whenever the supply fan does, pulls return air from the occupied spaces and pressurizes the diverting plenum in the rooftop unit. Air from this plenum either passes through the return air damper into the mixing plenum or exits the building through the relief damper. With a return fan configuration, the fan is physically in the return ductwork. In order to complete the ventilation loop, it has to run whenever the supply fan runs. Also, the return fan must be sized to support the maximum CFM of the return air at the worst case return static. Interestingly, this is probably not on an economizer day because supply airflow is lower. Rather, sizing needs to be done for a design day when supply airflow is at its maximum. Because the return fan is located in the return duct, one of the benefits is its ability to overcome high return duct static losses. One of its drawbacks is that it is always on and must always be controlled. Now let's look at a relief fan. In the relief fan configuration, the fan is located outside of the ventilation loop and only needs to operate when it is necessary to relieve excess building pressure. In some applications, when the rooftop unit is bringing in minimum ventilation airflow, local exhaust fans in the restrooms and exfiltration due to building pressurization may be sufficient to relieve all the air brought into the building for ventilation. In this case, no centralized relief is needed and the relief fan can be turned off. Since the relief fan is located outside of the ventilation loop, the energy benefits to the system are greatest when the fan is off. In many buildings, this could be any time the system isn't economizing. The disadvantage of the relief fan being outside of the ventilation loop is that the return duct static must be added to the supply fan. This will require a higher horsepower selection. Of course, building pressure can be controlled using either fan configuration. So, which is preferred? Both fan systems should be evaluated. But, generally, if the supply fan is capable of handling the pressure drop of both the supply and return air paths, then the relief fan configuration is preferred. As an example, the relief fan configuration works best in VAV systems that use an open sealing plenum for part of the return air path. When the pressure drop through the return air path is very high, as in some hospitals, again, evaluate both configurations. Use a return fan if the return air path adds more pressure drop than the supply fan can handle. The relief fan can often be turned off during non-economizer hours, while a return fan must run whenever the supply fan is on. Fewer hours of operation usually result in lower operating cost. Both systems should use low leak dampers. With a relief fan system, when the relief fan is off, the negative pressure diverting plenum may draw in outdoor air through the relief damper. With a return fan system, the opposite is true. The return fan pressurizes the diverting plenum, and conditioned air can leak out of the relief dampers. Low leak relief dampers help minimize both problems.
Next topic, evaporative condensing.
Packaged rooftop units use a vapor compression refrigeration cycle that includes an evaporator coil, one or more compressors, a condenser, and expansion devices. The overwhelming majority of packaged rooftop applications specify air-cooled condensers. The air-cooled refrigeration system depends on the ambient dry bulb temperature to subcool the hot gas produced by the vapor compression cycle. Propeller fans draw the outdoor air over a fin tube heat exchanger surface. The temperature difference between the hot refrigerant vapor flowing through the heat exchanger and the cooler dry bulb temperature of the outdoor air induces heat transfer, causing the refrigerant vapor to condense into a liquid. Air-cooled condensers are very popular because of their simplicity and convenience, and they're widely accepted as the most effective first-cost solution. Outside of an occasional cleaning, the air-cooled condenser requires very little maintenance. Evaporative cooled condensers are specified in far fewer packaged rooftop applications. While convenience and low first cost are major drivers for the application of air-cooled condensers, energy and demand kW savings are the major drivers for the application of evaporative cooled condensers. The trade-offs between low first cost and maintenance conveniences of the air-cooled condensers are the additional benefit of higher energy efficiency plus higher first cost and maintenance cost of the evaporative cooled condenser. Similar to an air-cooled condenser, refrigerant flows through tubes and outdoor air is drawn or blown over the tubes by a fan. The difference is that water is sprayed on the outer surfaces of the tubes. As the air passes over the tubes, a portion of the water evaporates. This evaporation process absorbs heat, causing the refrigerant vapor inside the tubes to condense into a liquid. The remaining water then gravitates into the sump, where it's recirculated by a high-flow pump. Typically, moisture eliminators are placed between the condenser fan and the water spray tower and at the condenser air inlets to prevent water carryover. The water that evaporates in this process must be continually replaced with fresh water. As the water evaporates, the dissolved minerals and water treatment chemicals become more concentrated in the sump. To minimize the levels of concentration, water may be continuously bled from the sump with an equal amount of fresh water added. Additionally, in areas that have an inadequate or costly water supply, or if the use of water for the purpose of air conditioning is restricted, air-cooled condensers are favored over evaporative-cooled condensers. As mentioned earlier, the major benefit of evaporative-cooled condensing is higher energy efficiency. Typical design condensing temperatures for air-cooled machines range between 115 and 130 degrees Fahrenheit. Typical design condensing temperatures for evaporative-cooled machines range between 85 and 105 degrees. the lower condensing temperatures produced by the effect of evaporative cool condensing reduce the amount of work required by the compressors. The system operates at lower head pressure and therefore reduces the compressor kW. In some systems, evaporative cool condensing can significantly reduce compressor kW, typically between 20 and 30%, and substantially increase energy efficiency over comparable air-cooled systems. A packaged rooftop unit applied in our previous scenario with evaporative condensing yields an energy efficiency ratio of 13.4, an increase of 22% over the high-efficiency air-cooled unit. Naturally, greenhouse gas emissions would further decrease with the benefit of higher energy efficiency. However, a thorough financial analysis should be conducted to determine the long-term benefits of the investment in evaporative cool condensing.
Next topic, hot gas bypass.
As Justin alluded to earlier, hot gas bypass is probably the device whose indiscriminate use results in more wasted energy than any other single refrigeration design issue I can think of. That isn't to say hot gas bypass should never be used, but for proper reasons, it should either be designed into a system or designed out of the system. Hot gas bypass was traditionally used on VAV systems at low airflow, low tonnage conditions to prevent frosting of the evaporator coil while the VAV controller allowed the compressors to cycle off through time delays. One of two things happened. Either the hot gas was literally set to prevent frosting, in which case it never came on because the suction pressure never got low enough to activate it, or it was set so high that it was activated quite frequently and affected the capacity of the unit at many operating conditions. In this latter case, a rule of thumb concerning hot gas bypass is that it will increase the stage of compression one step beyond a system without hot gas bypass. It isn't hard to comprehend the additional energy required to run a system one step higher than it may need to operate, even if this is just part-time. It's a rare case indeed to find a traditional VAV system that actually requires hot gas bypass. But if one is found, then the hot gas bypass by definition must work. In that case, it must control well and be well controlled so that it doesn't waste energy. That probably means it needs to be an electronic hot gas bypass system which is able to control with some accuracy. So that we provide sustainable systems for the future, and so that hot gas bypass can be avoided as often as possible, choose units that maximize the stages of compression, choose intertwined evaporator coils, never oversize rooftop tonnage, and protect against frosting conditions with evaporator defrost or frostat. And remember that the average supply air condition is what is important.
Next topic, fan-powered VAV and ECMs.
Heat generated by light fixtures warms the air in the ceiling plenum. Fan-powered VAV boxes use this warm air from the plenum as a form of energy recovery. In a parallel fan-powered VAV box, primary airflow is reduced as the cooling load decreases. When the box reaches its minimum airflow setting, the small fan activates to draw warm air from the ceiling plenum and mix it with cool primary air from the rooftop unit. If more heat is required, the heating coil can be activated. Parallel fan-powered VAV boxes can save energy because they use warm air from the ceiling as the first stage of heating. This delays the need to use new energy by activating the heating coil. The use of electrically commutated motors, or ECMs, in fan-powered VAV boxes has become increasingly popular due to several benefits. The first is energy savings. An ECM is a brushless DC motor that's more efficient than the single-speed, fractional horsepower motor technologies that have traditionally been used in fan-powered boxes. This chart compares the performance of a standard AC motor with that of an ECM at various airflows for a series fan-powered box. Although the efficiency advantage is less at the upper end of the application range for the motor, the performance of the ECM really shines at the low end. This efficiency difference allows ECMs to offer substantial energy savings. Of course, they cost more than their AC counterparts, but this added cost can be offset more quickly in applications that require a relatively high number of operating hours. For this reason, ECMs are more commonly used with series fan-powered boxes, in which the terminal fan operates whenever the zone is occupied. But even if a zone may not be a good candidate for this type of motor based solely on energy savings, the decision to use an ECM may be based on other benefits. The ECM allows for a greater airflow range for a given fan size. We saw this in the previous slide. If the usage of a zone is expected to change frequently, this ability to change supply airflow may avoid the need to replace the VAV box. An ECM is also capable of self-balancing to a desired airflow. This may eliminate additional balancing dampers or changes to downstream ductwork to ensure proper airflow. Finally, the soft start nature of the ECM allows the fan to ramp up slowly when activated. This minimizes the distraction of the fan cycling on and off in a parallel fan-powered box. But you want to consider the potential for disruptive harmonic currents. Determining whether harmonic currents will cause a problem in a particular building requires review of the electrical system before it's installed so that appropriate steps can be taken then.
Okay, so far the team has focused only on the equipment. All of the discussed strategies can be added to systems to help reduce system energy use. Remember that hot gas bypass is something we want to eliminate, if possible, since it is so inefficient. Next, on to alternative system designs. First up is Paul with single-zone VAV.
In a traditional multiple-zone VAV system, a temperature sensor in each zone modulates a VAV box to vary the volume of supply air delivered to that zone. At the same time, the central supply fan modulates to maintain pressure in the supply ductwork. On the other hand, a single-zone VAV system serves only one zone. No VAV boxes are used. Instead, a temperature sensor in the zone is used to directly vary the airflow delivered by the supply fan. And like a conventional VAV system, cooling capacity is modulated to maintain a discharge air temperature set point. Single-zone VAV is an excellent system for large, densely occupied zones that have variable cooling loads. Common examples include gymnasiums, lecture halls, arenas, auditoriums, and places of worship. Compared to a constant volume system that is often used for large zones such as these, a single-zone VAV system results in fan energy savings and less fan-generated noise at part load conditions. It also improves part load dehumidification because the system continues to deliver cool, dry air at part load conditions, which could save energy in the reheat region. Finally, the controls are relatively simple since there are no VAV terminal units to coordinate. Standard equipment can typically be used. In order to gain these benefits, the application must be suited to use single-zone VAV. So we need to consider the following. First, the loads throughout the zone need to be fairly uniform. A single-zone VAV system doesn't have the capability to satisfy simultaneous heating and cooling requirements. In addition, when the load in a large space isn't uniform, it may result in undesirable temperature variations in areas of the zone that are further away from the zone sensor. Second, design the air distribution system to accommodate variable supply airflow. Keep the supply duct as short and symmetric as possible. Systems with long or asymmetric duct runs are more susceptible to unequal airflows between diffusers. Size the ducts for low to medium air velocities to minimize noise generated in the ductwork, and use diffusers that prevent dumping at low airflows. Third, consider the need for heating in the zone. Typically, A source of heat is provided in the rooftop unit. When the zone needs heating, the rooftop unit stages heating capacity to maintain space temperature. In packaged DX rooftop units, the supply fan can typically turn down to about 30% of the design airflow. In a zone with a widely varying load, the sensible cooling load may become small enough that the required supply airflow is less than the minimum airflow that can be delivered by the supply fan. Under this condition, the zone will be at risk of being overcooled. One way to prevent overcooling is to reset the supply air temperature upward at low load conditions. This avoids overcooling the zone, but the amount of reset must not cause excess humidity levels in the zone. Finally, because a single zone VAV system is often used for densely occupied zones with a highly variable population, it's typically a good application for CO2-based demand control ventilation. CO2, which is produced continuously by the occupants, is diluted by the outdoor air. With CO2-based demand control, a sensor is used to monitor the concentration of CO2 in the zone. This concentration is then communicated to the rooftop unit and used to reset the intake airflow required to properly dilute the air in the zone. This reduces energy use by attempting to not overventilate the zone.
Next topic, hot gas reheat.
A VAV system typically dehumidifies effectively over a wide range of operating conditions because it continues to deliver cold, dry air at part load. However, controlling humidity levels isn't only a priority when the building is occupied. When indoor humidity rises too high during unoccupied times, one option is to turn on the rooftop unit and dehumidify recirculated air to 55 degrees or so. However, there's typically very little sensible load in the space at this time, so the reheat coils in the VAV boxes may be activated to prevent overcooling. If a hot water heating system is used, this also requires turning on the boiler and pumps. An energy-saving alternative is to equip the rooftop unit with hot gas reheat. When after-hours dehumidification is needed, the rooftop unit turns on and diverts hot refrigerant vapor, leaving the compressor, through a refrigerant-to-air heat exchanger that is located in the airstream, following the evaporator coil. Sensible heat is transferred from the hot refrigerant to reheat the dehumidified air leaving the evaporator. This strategy uses heat recovered from the refrigeration circuit to reheat centrally. It saves energy by avoiding the use of new energy to reheat remotely at the VAV boxes. It also allows the boiler and pumps to remain off.
Next topic, dedicated outdoor air systems.
In a conventional VAV system, the multiple spaces equation from ASHRAE Standard 62 requires the rooftop unit to bring in more outdoor air than simply the sum of the zone ventilation requirements. If, however, a dedicated outdoor air system is used, the dedicated unit conditions all the outdoor air for the system, then delivers it directly to dual duct VAV terminals that serve each zone. The ventilation damper in the dual duct box maintains the required quantity of outdoor air from the dedicated outdoor air unit, while the primary air damper regulates recirculated air from the VAV rooftop unit. Since the outdoor air is delivered directly to zone level VAV terminals, this is not considered a multiple space recirculating ventilation system. So the outdoor airflow delivered by the dedicated unit can be the sum of the zone ventilation requirements, which is typically less than what ASHRAE 62 would require of a conventional rooftop VAV system. In most applications, reducing outdoor airflow saves energy. Of course, the additional unit and duct system and the dual duct boxes do impact the installed costs.
So from a system design standpoint, single zone VAV is often used in systems today and provides energy reductions, especially when used in conjunction with demand-controlled ventilation. And there are more energy-efficient humidity control alternatives available today also. You know, when we speak of system design alternatives, some of them sure feel a lot like control options. That line between system design and system operation is becoming fuzzier all the time. The bottom line is that the sensors and controls need to be installed for the system to operate efficiently. Okay, speaking of controls, let's ask the team to cover some optimized system controls. First up is John with Economizer controls.
An Airside Economizer is a common energy-saving control strategy that uses outdoor air as a source of free cooling whenever possible. When the dry bulb temperature of the outdoor air is colder than the supply air, the controller modulates the positions of the outdoor and return air dampers so that the mixture provides supply air at the desired temperature. In this modulated economizer mode, the outdoor air is cool enough to handle the entire load, so the compressors are shut off. This saves cooling energy. When the temperature of the outdoor air rises above the current supply air set point, the system needs more cooling capacity than the outdoor air alone can provide. In this integrated economizer mode, the outdoor air dampers remain wide open and the rooftop unit activates compressors to provide the balance of the cooling capacity needed. This also saves energy by reducing the cooling load on the compressors. Eventually, as it gets hotter outside, the outdoor air damper is closed to minimum position and the compressors provide all the needed cooling. This decision to disable economizer operation is typically made automatically by comparing the condition of the outdoor air to a set point called the high limit shutoff setting. The selection of the economizer control strategy and shutoff setting have an impact on energy use. Our May broadcast discussed several economizer control strategies, but I'll just review 3 of them that are probably the most common to rooftop VAV systems. Fixed dry bulb control compares the dry bulb temperature of the outdoor air to a predetermined high limit shutoff setting and disables the economizer whenever the outdoor dry bulb is above this limit. This method is simple and relatively inexpensive. But if the shutoff setting is too high, this control strategy can bring in cool but humid outdoor air, which may actually increase mechanical cooling energy. Fixed enthalpy control uses sensors to measure both the dry bulb temperature and humidity of the outdoor air. The controller then calculates the enthalpy and compares it to a predetermined high limit shutoff setting. The economizer is disabled whenever the outdoor air enthalpy is above this limit. This method requires an added humidity sensor, but for a VAV system, in most climates, fixed enthalpy control saves more cooling energy, so it might be worth the added first cost. However, in hot and dry climates, bringing in 100% outdoor air can actually increase cooling energy, even if the outdoor air enthalpy is lower than this limit. Differential or comparative enthalpy control uses sensors to measure and calculate the enthalpy of both the outdoor and return air streams, and uses as much of the lower enthalpy air as it can to satisfy the cooling load. The economizer is disabled whenever the outdoor enthalpy is higher than the return air enthalpy. The installed cost of differential enthalpy control is higher than for the other control methods because it requires humidity sensing for both outdoor and return air. But in a VAV system, it typically results in the most cooling energy saved. For example, we use Trace 700 to analyze an office building located in Cincinnati, Ohio. ASHRAE 90.1 2004 does not require an economizer for this location. In this example, the differential enthalpy economizer resulted in the most energy savings, about 11% compared to a system with no economizer. Although for this particular building and climate, the other, less expensive methods did nearly as well. Of course, climate, building usage, and utility costs impact the operating cost differences of these economizer control methods.
Next topic, optimal start-stop.
In many applications, a simple time clock or time of day schedule is used to start and stop the HVAC system. This simple set it and forget it logic is reliable and typically works without issue. During the unoccupied hours, the system is shut off and the temperature is allowed to drift away from the occupied set point. The time at which the system starts in the morning is typically set to ensure that the indoor temperature reaches the desired occupied set point on either the coldest or warmest morning of the year. Not a very scientific approach, but no one has to think about what's happening with the system or when it happens. The result is, for most days, the system starts much earlier than it needs to. This control method increases the number of system operating hours and energy usage. However, there is a more energy efficient method. An alternative is a strategy called optimal start. As Justin mentioned earlier, ASHRAE 90.1 requires an optimal start strategy when the system design airflow is greater than 10,000 CFM. For optimal start logic, a building automation system is used to determine the length of time required to bring the zones from their current unoccupied state temperatures to the occupied set point temperature. So, the system waits as long as possible before starting. This minimizes system runtime and prevents the zones reaching the occupied set point temperature prematurely. The appropriate comfort set point is reached just in time for occupancy. This optimal starting time is determined using the difference between the actual zone temperature and the occupied set point, and comparing this difference with the historical performance of how quickly the zone is able to warm up or cool down. This strategy reduces the number of system cooling and heating hours and saves energy by avoiding the need to maintain the indoor temperature at the occupied set point, even though the building is still unoccupied. A similar strategy is optimal stop. As I mentioned earlier, at the end of the occupied period, the system is shut off and the temperature is allowed to drift away from the occupied set point. However, the building occupants may not mind if the zone temperature drifts just a few degrees before they leave for the day. Optimal stop uses the same BAS to determine how early the heating and cooling can be shut off for a zone to allow the zone temperature to drift only a couple of degrees from the occupied set point. The supply fan continues to operate and the outdoor air damper remains open to continue ventilating the building. Only cooling and heating functions are terminated. This strategy also reduces the number of hours that the system must operate and saves energy by allowing the indoor temperature to drift early.
Next topic, fan pressure optimization.
Let's investigate a fan control strategy which can save energy. In a VAV system, as the cooling loads in the zones change, the VAV boxes modulate to vary the airflow supplied to those zones. This causes the pressure inside the supplied ductwork to change. The rooftop unit modulates the airflow of the supply fan to maintain set point of the supply duct static pressure. In many systems, the pressure sensor is located about 2/3 of the distance down the main supply duct. But when no zone is at design cooling load, none of the boxes are wide open and the system is generating more static pressure than is required. When communicating controllers are used on the VAV boxes, it's possible to optimize the static pressure control function to provide just enough pressure in the duct and minimize fan energy consumption. Each VAV box controller knows the current position of its air modulation damper. The BAS can continually poll these individual box controllers, looking for the one with the most open damper. The fan static pressure set point can be reset lower. The VAV box, in turn, will be nearly wide open in order to maintain the airflow necessary to cool the space. The result is that the supply fan generates only enough static pressure to push the required quantity of air through this critical VAV box. This concept, which we call fan pressure optimization, has several benefits. First is that it reduces supply fan energy use. At part load conditions, fan pressure optimization allows the supply fan to operate at a lower static pressure and therefore use less energy. Second, lowering duct static lowers sound levels. Because the supply fan doesn't need to generate as much static pressure, it typically generates less noise. And with lower pressures in the supply ductwork, the dampers in the VAV boxes will be more open, resulting in less noise generated at the boxes. A third benefit is the reduced risk of fan surge. By allowing the fan to operate at lower pressures at loads requiring reduced airflows, the fan operating point is kept further away from the surge region than when using conventional duct pressure control. The fourth benefit is the ability to control from a unit-mounted sensor. Because fan pressure optimization uses the position of the VAV box dampers to reset the fan set point, the static pressure sensor can be located anywhere in the supply ductwork. This presents the opportunity to have it factory installed and tested at the outlet of the fan inside the rooftop unit. In this location, it can also serve as the duct high pressure sensor, protecting the ductwork from damage in the event of a fire damper closing.
Next topic, supply air temperature reset.
It's tempting to raise the supply air temperature at part load conditions in an attempt to save compressor or reheat energy. There are applications where the temptation is worth the reward. However, this practice should not be used indiscriminately. Let's take a look at the effects of supply air temperature reset. First of all, increasing the supply air temperature reduces compressor energy because it allows the compressor to operate at a warmer suction temperature. This equates to a higher suction pressure, which reduces the compressor lift and correspondingly reduces compressor kW. In addition, supply air reset increases the benefit of an Airside Economizer. Using a reset strategy, when the outdoor air is cooler than the supply air set point, the compressors are shut off and the outdoor and return air dampers modulate to deliver the desired supply air temperature. A higher supply air temperature set point allows the compressors to be shut off sooner and increases the number of hours when the economizer provides free cooling. For those zones with very low cooling loads, where the supply airflow has been reduced to the minimum setting of the VAV box, raising the supply air temperature also decreases the use of reheat energy. However, because the supply air is warmer, those zones that require cooling will need more air to offset the cooling load. This increases supply fan energy. Finally, in non-arid climates, warmer supply air means less dehumidification at the coil and higher humidity levels in the zones. So, if dehumidification is a concern, use this strategy with caution. This slide contains some general guidance on when and when not to use supply air reset. Conditions that favor using reset include mild climates that have many hours when the outdoor dry bulb temperature is below 60 degrees Fahrenheit. In this type of climate, the economizer-related benefits likely tip the scales in favor of supply air temperature reset. In systems with VAV terminal units that have minimum airflow settings higher than 30% of design airflow. Higher minimum airflow settings increase the likelihood that reheat will be needed to avoid overcooling the zones. Efficient air distribution system design. Low pressure losses cause less of a fan energy penalty for the higher airflows that result from raising supply air temperature. Systems with interior zones that have varying cooling loads. The variable loads may allow these zones to be satisfied with a warmer supply air temperature. On the other hand, conditions that reduce the potential to save energy with supply air reset include hot or humid climates that have relatively few hours when the outdoor dry bulb temperature is below 60 degrees Fahrenheit. Humidity is a condition that adversely affects comfort. Systems with efficient part load fan modulation. Using a VFD on the supply fan and a fan pressure optimization control strategy often make it more advantageous to reduce supply airflow and save fan energy rather than increase airflow and save compressor energy. Inefficient air distribution system design and systems that serve some zones that have nearly constant cooling loads. These zones will need design airflow during all occupied hours, limiting the ability to raise the supply air temperature. Investigate using a separate system to serve these zones. When used, this reset strategy should be designed to minimize overall system energy use. This requires considering the trade-off between compressor, reheat, fan energy, and space humidity levels. These competing issues are often best balanced by first reducing supply airflow, taking advantage of the significant energy savings from unloading the fan. Then, after fan airflow has been reduced, raise the supply air temperature to minimize reheat energy and enhance the benefit of the Airside Economizer. While one could concept numerous control schemes for supply air temperature reset, the simplest approach is probably most commonly applied. That is, to reset the supply air set point based on outdoor temperature. This slide shows an example of a supply air reset strategy that is based on outdoor temperature. The reset high limit is set to 70 degrees Fahrenheit. When the outdoor dry bulb temperature is warmer than 70 degrees, no reset takes place, and the supply air set point remains at its design value of 55 degrees. At temperatures above 70 degrees, the outdoor air provides little or no cooling benefit for economizing, and the cooling load in most zones is likely high enough that reheat is not required to prevent subcooling the space. Additionally, the colder supply air temperature allows the system to provide sufficiently dry air to the zones, improving part load dehumidification. Then, when the outdoor dry bulb temperature is between 60 and 70 degrees Fahrenheit, the supply air set point is reset at a 2-to-1 ratio. That is, for every 2 degrees change in the outdoor temperature, the supply air set point is reset upward 1 degree Fahrenheit. In this range, reset enhances the benefit of the economizer and is likely that some zone level reheat can be avoided. Finally, when the outdoor temperature is colder than 60 degrees, no further reset occurs, and the supply air set point remains at 60 degrees Fahrenheit. Limiting the amount of reset to 60 degrees allows the system to satisfy cooling loads in interior zones without needing to substantially oversize VAV terminal units and ductwork. Alternatively, some strategies reset the supply air set point based on the temperature in the critical zone. In this case, the critical zone is the one that is most at risk of overcooling, which would require activating local reheat. A building automation system monitors the temperatures in all the zones. The critical zone is the one with the temperature closest to its heating set point. Based on a signal from the BAS, the rooftop unit resets its supply air temperature set point to prevent the critical zone from needing reheat. For interior zones that will likely have near constant cooling loads during occupied periods, calculate design airflows for those zones based on the warmer reset supply air temperature. For our example, this would be 60 degrees Fahrenheit rather than 55 degrees. While this may require larger VAV terminals and ductwork, it allows supply air reset to be used during cooler weather and still provides the needed cooling for these weather-independent interior zones. Also, design the air distribution system for low pressure losses and use the fan pressure optimization strategy to minimize the penalty of increased fan energy when the supply air temperature is raised. When considering using supply air temperature reset in a rooftop VAV system, first, analyze the system to determine if the savings in compressor and reheat energy will outweigh the increase in fan energy. If higher space humidity levels are a concern, consider either disabling reset when it's humid outside or provide one or more zone humidity sensors to override the reset function if humidity in the zone exceeds some maximum limit.
Next topic, ventilation optimization.
In a typical rooftop VAV system, the rooftop unit delivers fresh outdoor air to several individually controlled zones. Now, as we mentioned in our broadcast last November, the 2004 version of ASHRAE Standard 62 now explicitly permits dynamic reset of outdoor airflow as operating conditions change. The standard lists some examples of dynamic reset, including these two. You can reset intake airflow in response to variations in zone population, which is often referred to as demand-controlled ventilation. DCV is commonly implemented using carbon dioxide sensors, but occupancy sensors or time-of-day schedules can also be used. In addition, you can reset intake airflow based on variations in ventilation efficiency, which we refer to as ventilation reset. The goal of each of these strategies is to bring in only the minimum amount of outdoor air needed for the current system operating conditions. In most applications, reducing the outdoor airflow will save energy. In most rooftop VAV systems, the best approach often combines several demand control ventilation strategies at the zone level, using each where it best fits, and then couple these with ventilation reset at the system level. With this strategy, CO2 sensors are installed only in those zones that are densely occupied and experience widely varying population. In this example, CO2 sensors are installed only in the conference room and the lounge. These are good candidates for CO2 sensors and provide the most bang for the buck. However, zones that are less densely occupied or have a population that varies only a little, such as private offices, open plan office spaces, and many classrooms, are probably better suited for occupancy sensors. In this example, each of the private offices has an occupancy sensor. When it is unoccupied, the controller lowers the ventilation requirement for that zone. Occupancy sensors are relatively inexpensive. They don't need to be calibrated and are already used in many zones to control the lights. Finally, zones that are sparsely populated or have predictable occupancy patterns may be best controlled using a time-of-day schedule in the building automation system. This schedule can either indicate when the zone would be normally occupied versus unoccupied, or may even be used to vary the zone's ventilation requirement based on anticipated population. These various zone-level DCV strategies are used to reset the ventilation requirement for their respective zones for any given hour. This zone-level control is then tied together using ventilation reset at the system level. In addition to resetting the zone's ventilation requirement, the controller on each VAV terminal continuously monitors primary airflow being delivered to the zone. Then, the BAS periodically gathers this data from all the VAV terminals and solves the ventilation reset equations to determine how much outdoor air must be brought in at the rooftop unit to satisfy all the zones served. Finally, the BAS sends this calculated outdoor airflow set point to the rooftop unit, which modulates a flow measuring outdoor air damper to maintain this new set point. Combining demand control ventilation at the zone level with ventilation reset at the system level has the following benefits. It can ensure that each zone receives the proper amount of ventilation without requiring a CO2 sensor in every zone. CO2 sensors are used only in those zones where they will bring the most benefit. This minimizes installed costs and avoids the periodic calibration and cleaning required to assure proper sensor operation. For the other zones, occupancy sensors and time-of-day schedules are used to reduce ventilation. Next, it enables documentation of actual ventilation system performance. The VAV controller for each zone communicates the ventilation airflow for every zone to the BAS, even for those zones that do not have a CO2 sensor. So you can generate reports showing ventilation CFM in every zone for every hour. Finally, the system-level ventilation reset equations are explicitly defined in an industry-wide standard, ASHRAE 62. So they're defendable.
Team, thanks for taking us through those system-level controls. We've now examined what can be done from an equipment standpoint, different system designs, and controls. But this broadcast is not about those specific topics. It's about energy-saving strategies. So this brings us to the real question. How much energy can be saved by using these different strategies? That's one of the reasons Justin is on the panel today. He took some examples and is going to share them with us.
So we've talked about several energy-saving strategies today. Of course, the impact of any one of them on the operating cost of a specific building depends on climate, building usage, and utility costs. Building analysis tools like Trace 700 can be used to analyze many of these strategies and convert energy savings to real operating cost dollars that can be used to make financial decisions. To use as an example for today's broadcast, we modeled an office building and compared a typical rooftop VAV system to a more optimized system. For the optimized system, we added the optimal start, supply air temperature reset, and ventilation optimization control strategies we discussed today. The supply fan is controlled based on fan pressure optimization rather than on a fixed set point in the ductwork. The rooftop unit contains a total energy wheel to precondition the outdoor air and uses comparative enthalpy economizer control rather than fixed dry bulb control. Finally, the perimeter zones are equipped with parallel fan-powered VAV boxes rather than VAV reheat boxes. The results show that there is potential to improve the energy efficiency of rooftop VAV systems. The orange column to the left for each city is the base case, and the green column to the right is the optimized system. The y-axis is overall HVAC energy consumption, shown as a percentage of the base case. The optimized rooftop VAV system reduced the HVAC energy by 35% for the building in Atlanta, by 30% in Los Angeles, and by 45% in Minneapolis. We see a lot of rooftop VAV systems that are similar to this typical base system, but in some ways, this base system doesn't even meet the minimum requirements of ASHRAE standards 90.1 and 62. For example, in DDC VAV systems, fan pressure optimization is required by 90.1. So here are the results comparing the same optimized system to a base system that does comply with these standards. Here are the optimized rooftop VAV system reduced HVAC energy by 24% compared to the 90.1 and 62 compliant system in Atlanta, 19% in Los Angeles, and still by about 45% in Minneapolis. As I said, the impact of these strategies on operating costs can vary significantly from building to building. That's where analysis tools like Trace 700 can help.
So those savings are available on day one when the system is designed, installed, commissioned, and working properly. How do you sustain that performance? Studies show that taking existing systems and simply making them operate as intended can save up to 35% of the energy use. While this may seem obvious, it's critical that the system performance be sustained. So Phil's going to take us through talking about rooftop system maintenance.
Regularly scheduled maintenance helps to ensure continued energy savings benefits from your investment. Performing these often neglected preventative maintenance procedures can keep your system operating at peak performance. Remember to always have airside maintenance performed first. Airflows outside the design CFN can cause maladjustments to the refrigeration side. We recommend scheduling periodic filter inspections based on your application environment. Filters should be cleaned or replaced as necessary. An additional 1/10 of an inch static pressure drop induced by dirty filters can increase the supply fan kW by 7%. Inspect condensate drains and traps whenever filters are inspected and cleaned as needed. This is just good practice. Inspect fresh air and return air damper mechanisms. Clean the blades as necessary. Damaged or loose damper linkage can cause excessive air leakage. You could be wasting energy by unnecessarily conditioning excess fresh air. Check supply relief motor and fan shaft bearings. Lubricate, repair, or replace as necessary. Inspect the evaporator and condenser coils for dirt buildup. Restrictions on either coil increases pressure drop and motor kW. Clean the coils as necessary. Check condenser fan rotation for free movement. Check the bearings for wear. Verify that all fan mountings are secure. Again, this is just good practice. And finally, probably the #1 energy robber improper refrigerant charge. Improper charging can decrease energy efficiency and capacity. Overcharging the system decreases superheat and increases subcooling. A system overcharged by 10% can increase compressor kW by approximately 3.5% at design operating conditions. An undercharged system increases superheat and decreases subcooling, resulting in capacity loss. Loss of capacity means that mechanical cooling hours increase to maintain temperature. It is critical to maintain the refrigeration system balance point by charging according to the manufacturer's superheat and subcooling temperature recommendations. And you should always follow the manufacturer's charging process, which is usually outlined in the Equipment Installation Operation Manual. In summary, we all know that these preventative maintenance procedures should be routinely performed, and we are covering many system efficiency enhancing concepts today that, when properly applied, can make significant improvements in energy savings. However, absent a well-defined approach to system maintenance, the value of the investment in higher system efficiency can and will be compromised.
Great job, team. Now let's move on to our question and answer portion of the broadcast. If we don't get to yours while we're on the air, we'll get the answers out within 4 weeks. Now, John, the first one's coming to you. It's a little bit involved. 90.1 requires reduced airflow for reheat systems, despite diffusers being sized for full flow. This can result in improper throw and is especially difficult in cold climates with exterior zones. How could we use diffusers in a heating situation for a VAV system to give better occupant comfort?
Okay. A few different things there. First of all, I had to mention in very cold climates, sometimes it's advantageous to use baseboard perimeter heat as well for that envelope heat loss. I'm assuming we're kind of moved on that might not be an option in this particular application. So if you are using heat provided from overhead diffusers, Trane has a VAV air conditioning clinic that outlines some application guidance on how to handle perimeter heating loss and how to locate diffusers. I don't have those numbers off the top of my head, but I'll include that in our write-up for these answers to show you those different ranges, whether it's dumping that or blowing that air directly on the perimeter zone versus putting it in the center of the space. Outside of that, the type of diffuser is pretty important or critical to that. High aspiration diffusers, things like linear slot diffusers, help that because they have a tendency to draw in a lot of room air and help increase the actual recirculated airflow being recirculated in the room, not just the air actually coming through the diffuser. So the third is the diffuser selection itself.
Thanks, John. Paul, this one's coming to you. There are actually 2 questions. The first one's pretty detailed about how Frostat works instead of hot gas bypass, but I think this one's a good one here. Can you give an example when hot gas bypass might be a good choice?
Sure, Mick. There's 2 design parameters which come to mind which lend themselves well to hot gas bypass. One is if it's a high percentage of outdoor air. The other is if it's precise temperature control. Now, having said that, let me give you an example. Let's say there's a rooftop unit which is supplying air to a laboratory, and this laboratory has multiple exhausts on it. As the exhausts turn on, it has to have different airflow. Well, that system may need hot gas bypass to operate throughout the operating envelope of the system.
Okay. John, this one's coming over to you. Does it make sense to use demand-controlled ventilation and energy recovery at the same time?
Okay. You can use them both at the same time. The challenge in using them both at the same time is that as you reduce the amount of outdoor air through demand control ventilation, obviously you have now less outdoor air coming through one side of the wheel and less benefit to provide to that outdoor air. The second thing that people don't think about as often is, we mentioned earlier about in a VAV system you have some local exhaust from restroom fans, some leakage because of building pressurization. That's kind of a constant amount of air leaving the building locally. So how much air comes back centrally and goes through the exhaust side of the wheel is reduced as you bring less air in through the intake. You could get to a point where you're putting very little air through the exhaust air side, so you don't have anything to recover energy from. So there's certainly a trade-off there. If you're doing both, it's probably got to be a pretty high percentage of outdoor air or a real severe climate with a lot of hours in those cases to make sense.
Thanks, Murph. Justin, one for you. Can you give a definition of the deadband and an example of cooling and heating set points that might be used to satisfy 90.1?
Okay. Deadband is the temperature range between the cooling and the heating set point. And it's that point where there's no mechanical heating or cooling taking place. A good example would be a cooling set point of 75 degrees and a heating set point of 70 degrees. That at any temperature between those two, the HVAC equipment is turned off, which helps minimize energy costs. And this can be achieved with either a mechanical or digital thermostat.
Super. Murph, another one coming to you. You seem to be the winner today. Are there economical ways to use a building automation system to detect failures of economizers?
And to figure out what my prize is. There certainly are ways you can add some kind of automatic routines in there to determine if actuators are working properly. Sensors are a little bit harder to do that with because you might have to have multiple sensors in place, but just having a routine saying open up the outdoor damper or close it and see what the change is in a mixed air temperature versus outdoor temperature is one way to kind of do a periodic check on that. Not very commonly applied, but certainly talked about a lot more in the industry in terms of ways to do that. Economically is always a challenge because it might take some programming in the field to make sure it's working properly and testing it out over time.
Okay, Murph, boomerang's coming right back. We'll figure out the price later on. Why use minimum VAV airflow settings which lead to overcooling and increase the need for reheat when increased occupancy will automatically increase airflow and demand-based ventilation will adjust the outdoor air as needed?
A lot of times the minimum setting on a VAV box is done for a couple different reasons. One might just be air distribution in the space, depending on the type of diffusers that are used. Or the duct system, it might need to maintain a certain amount of air, CFM, at minimum to get proper air distribution through there. The other reason is ventilation driven, trying to keep it above the minimum ventilation requirement for that space. I agree with you, having lower minimums helps prevent overcooling in that cooling mode. Sometimes people will use a lower minimum during the cooling mode and then move that up higher during the heating mode because of minimum requirements over electric heating coils, things like that, or increased air distribution. So a couple different minimum settings might be one way to achieve that.
Okay. Paul, one for you. Can you talk about when it might be better to use a bypass VAV system instead of a true VAV system with a variable frequency drive for packaged rooftops? Specifically, can we help avoid coil frosting?
I got to think about that one. I'm not so sure which type of bypass we're talking about, but if both systems are controlling discharge air temperature, it should be that both systems turn on and off compressors to avoid frosting.
Okay, thanks. Short and sweet. There are a bunch of questions that are pretty involved from a control standpoint that I think we're going to need to answer offline, but I'm going to throw one back to you, last one on air, Murph. How would the dual duct box be controlled on a dedicated outdoor air system?
Okay. The configuration I showed had a dedicated unit bringing all the outdoor air in and delivering it to multiple dual duct boxes for each zone. In that case, that airflow modulation damper that's connected to the dedicated outdoor system would be controlled to bring in the required outdoor airflow only. So you'd have a flow setting on there and control it to that. The other damper, taking air from the recirculating VAV rooftop unit, is controlled based on space temperature as it would be in a normal single duct type VAV system.
Okay, team, I can share with you that we do have some involved questions that we'll be answering in the next couple weeks, and we'll get back to you. But now it's time to wrap up today's broadcast. Our panel today covered equipment configuration strategies, designs, and control methods. Justin took us through one way to analyze the available savings, and Phil reminded us how to maintain the systems and sustain that high system efficiency. There are a number of publications related to today's broadcast, including John's new Engineer's Newsletter addressing rooftop VAV systems. We put together a bibliography detailing those pieces, and it's available from your local site coordinator. Past broadcasts are available on tape or DVD, depending on the vintage. Please check out the website information on specific broadcasts. And we thank you in advance for filling out an evaluation before you leave. And speaking of feedback from them, we've used your input from past broadcasts, and the E&L broadcast schedule for 2007 is set. In February, we'll look at how heat recovered from chillers can be implemented in systems to reduce energy use and cost. There's been an increased use in these systems, and there's a lot to share. In September, we'll cover many methods of humidity control. Some of them have been touched on in past broadcasts, but we'll go into more depth in the fall broadcast. Finally, we've all heard of and probably been to a number of lead-based training events that cover the requirements. But often, our applications engineering group is asked to share the systems, controls, and concepts we've seen used on particular jobs. So our final broadcast in November will cover several LEED certified projects and how they achieved credit points within those sections that HVAC systems affect. Thank you very much for joining us here today. Come on back in February.